Calc, it's Miss Marshall here. I want to take a little bit of time and we're going to bust up 3.3 into a couple of different days. Some of this we're going to try to do in class with you guys, basically Google meeting in like we've done for the last couple of days, trying to get you guys to join us for a live version of this conversation of implicit differentiation. But I'm going to create a quick video here for those of you that could not join us with a Google Meet and need to have this particular lesson done at home. So the implicit differentiation is really kind of an important piece that we're going to work with several times in calculus. So it's really important that you understand how to work with that. Implicit differentiation is usually a derivative. It is a derivative type of way of looking at a function, but specifically when we don't have this function in y equals or an f of x equals form. So we said, like, recall, what does it mean to implicitly define a function? So if you remember from some pre-calculus conversation, way back at the beginning of pre-calculus in chapter 1, we talked about this kind of language of implicitly defining a function. And this occurred when you guys were given relationships in algebra, like the circle, and you knew that the circle was not a function. And we asked you to implicitly define that function by taking a couple of moments to get y by itself and to get a y equals scenario. And when we do that, you understood things like subtracting that x squared on both sides, taking square roots. And we would talk a lot about the fact that there's this positive square root version that comes out, but then there's also a second version of that. So when we define the function itself, we had to do it in two separate parts. So if I took a circle and thought about the graphical piece of that and recognized that a circle fails that vertical line test, so it's not a function, but instead I could define that as a separate top piece and then another separate bottom piece. And each of those represented kind of that different part of the implicitly defined function. So the same thing is going to occur in calculus. And if you think about this particular type of graph, if I were to ask you to maybe create an equation of a tangent line or to tell me what is the derivative of this particular type of circle, I mean, hopefully it would be obvious to you right now that I absolutely could find an equation of a tangent line to this graph at a certain spot. But the problem is that if I were to just ask you something like, what's f prime at 3, and I'm making up some, oh, I probably shouldn't use 3, sorry, let me go f prime at 2, then that particular location, actually there's two y values. So which one am I talking about? Okay, what is the derivative at 2 when I could have two pieces? And if I got y by itself down here and implicitly defining them, I could take the derivative of this guy and have one of those answers, the derivative of this guy, and have the other answer. And so I could work with both of those. And I have those separation pieces, so that works. But unfortunately, we also have a lot of relations or a lot of equations in mathematics that getting y by itself is just not something that's always possible to do. So does that mean that I can't take a derivative? And the answer is no. So what we're going to do here is teach you guys how to do derivatives of functions where y is really kind of embedded in the equation somewhere without also asking you guys to constantly get y by itself, so that you're looking at two totally separate functions and working with those differently. And that's what implicit differentiation is. Here's a few other examples of some equations that we know or that maybe we've recognized in our algebra series. We just talked a little bit about the circle. I mean, this is a line, but y is not by itself. Y is in the middle of that. Here we've got a parabola that actually opens sideways. So we did a little bit in pre-calculus with some conics. And then we got this friend, look at that one, where you've got an x squared and an xy term and a y squared term, also a part of some of our conics conversation. All of these are some examples of equations that the y is really not by itself, it's embedded in there. And definitely 3 of those 4, getting y alone is not a big deal. So then the question becomes, what about derivatives? Okay, so let's get started on this taking a derivative of this. This is what we call implicit differentiation. How do we differentiate these? If we can solve for y, no problem, we'll go ahead and use that. If not, here is going to be our ruling today. It's kind of awkward, so I want you guys to make sure that you're waiting a little bit until we go through a couple examples before you really grasp what's going on here. But here's what we're going to do. We're going to differentiate, aka we're going to take the derivative of both sides of the equation separately. We're going to treat y as a function of x, and x's are going to be our variables. Since y is going to be a function, when we take a derivative of y, we're going to pretend like we don't really know what that y function is, so we're going to be using a chain rule. That's the part that's weird. Okay, so that's the part where I want you to hang on, write it down right now, hold off on it until you see a few things in action, and it should hopefully click for you. The resulting equation that we're going to do when we take the derivative on both sides, it's going to have some x's in it, some y's in it, some dy dx's, and then we are going to sometimes solve for dy dx and get that by itself. Sometimes we're not going to be able to solve that, and it's okay because we may not necessarily need to do that. Okay, so we're going to have some definite, interesting looking things today. Keep an open mind and be patient as you go through this because this is definitely the first time. Just a quick little comment. I'm not really certain why this x and this x, okay, those are some semicolons. So just like right here in this definition, this and this are some semicolons. So at first, I know that students think that that's a prime in there. That's not a prime. That is a semicolon. Okay, so just as a heads up, and I know we always have a student that asks, what's that little dash mark with the x? That's not, it's a semicolon. Okay, so FYI. All right, so let's look at, I know maybe some of you are still copying, pause, you can finish copying, but let's look at these couple of examples here. We're going to start off with two pretty simple examples and go through that process, and then we'll look at some more challenging ones here in a second. Some of it will extend into tomorrow's lesson as well. Okay, so we're going to find dy dx for this equation. Now this is one where we could take and get y by itself, but we're not going to. So here's how this is going to work. We're going to take the derivative of the x side, and derivative of x is 1. So we got that going for us. The other side, okay, the derivative of y squared, what we set up here in the directions, we're going to treat y as some function. Okay, so what that kind of means is that we have some function squared. We don't know really what that function is. Okay, obviously, we could find it technically by getting y by itself, but we're going to pretend like it's unknown. Okay, so then when we take the derivative of that side, we're going to keep and use y as the gut, but then we're going to have to use this chain rule scenario in order to take the derivative of the gut. So the derivative of this side is going to be 2y, okay, because we're going to keep the gut there, and then we would take like the actual derivative of the gut, which is a dy dx. So whatever the derivative of that y function, it would be called dy dx. Like I said, this is weird the first time through, so hang on. We'll go through a few examples and you'll catch on, don't worry. Okay, so y is a function. The derivative of y is dy dx, so we're tacking that on as a chain. Okay, so pop the 2 out front, keep the guts the same, tack on the actual derivative of the gut. If, maybe this might help before we continue, if this would have been y to the third, okay, and that's what we were taking the derivative, don't worry, we've got some of those coming up. It would be, the derivative would be 3y squared dy dx. Sometimes just seeing that separate might be an aha moment for you, where you're like, okay, I'm kind of getting it a little bit. Okay, but we take that power, pop it up front, keep the gut the same, drop the power by 1, and then tack on the derivative of the gut. Okay, so we'll keep practicing, don't worry. Okay, so now we're back to this problem here, okay, and we want to take a moment and get dy dx by itself. These are all multiplied by each other, so all I need to do is divide, okay, by that 2y on both sides. So we end up with the statement that dy dx, or the derivative of y, is equal to 1 over 2y. And this is going to be a final answer, by the way. This is a final answer. Now, if this sort of helps, and I don't want to confuse you with adding more to your plate, but I want you to think about, for a moment, if we saw something like this dy dx or y prime equals 1 over 2y, and remember that in our differential equation section where we talked about how the solution to that is the square root, and we had that conversation, look over here, what will happen if we get y by itself? Okay, well, y equals plus or minus the square root of x. So there should be a little bit of a connection for some of you out there to go, oh, okay, yeah, if I took the derivative of that, I would get, okay, 1/2 and then x to the negative 1/2 power, which pops to the bottom. So there's some connections there just to get you to think through some of that work. The beauty of keeping it as a differential, or excuse me, as an implicit differentiation is I don't have to worry about this plus or minus and having to do two different derivatives. All I have to care about over here is making sure that I just know what y values are. Okay, so some definitely different things to understand here in today's lesson. Okay, let's try another one right below this. Okay, we'll keep practicing things over and over again. Okay, find dy dx for this equation. Okay, so this particular second example, oops, sorry, jump maybe a little bit much. Okay, this first thing, we have 3x times y. Now, since y is technically some function that we don't know, this is actually a product. So we're going to need to treat it with a product rule. The first part is 3x, the second part is y. So when we do the derivative of this first term, we're going to stick with the product piece. So the product rule, derivative of the first is 3 times the second, which is y, plus the first, 3x, times the derivative of the second. Now the derivative of y is dy dx. So we put that there. We don't need the y this time. It's not y dy dx, because y is not a gut. Remember, up here, y was a gut, and that's why the y was there. But now it's not a gut, it's just a function. So once again, derivative of the first times the second plus the first times the derivative of the second. Okay, that's all for the 3x term. Now we go to the plus, and then derivative of 2x is 2, because x is the variable there. And the derivative of 5 is 0. Remember, derivative of any constant is just a 0. So now we have this particular equation. And our job here is to find dy dx. So we're going to get dy dx by itself. So I'm going to take a moment, subtract the 2 and the 3y, and I'm going to bring those both onto the other side. And then I'm going to divide both sides by 3x. So dy dx equals negative 3y minus 2 all over 3x. And this is my derivative. Now, I like this particular problem because I think that this is a little bit of a better understanding when connecting it to that little circle graph that I told you guys about earlier. So keep in mind that it's very common for you guys to have a derivative that's done implicitly that contains both x's and y's. Okay, and the reason for this being so popular is just like that circle. Remember what I said a minute ago, that if I have a circle, I might have a derivative at one spot and another spot in the same x's. So I usually will have to know the xy points for which one I'm talking about, and because I have maybe the same x with different y's, it should sort of make sense why our derivatives also contain x's and y's. Sorry about that. So we're going to need to be careful as to know more than just what the x's are when we do implicit differentiation. Okay, really nice. All right, let's look at a couple of other things here before we wrap up. So those were a couple of the basics. We're going to look at one more example, kind of, before I turn the screen, I'm going to warn you, this is a little bit of a big equation, so don't panic. We're going to take step-by-step stuff, but I know at first sight, students go, what? Okay, that's a lot of stuff. Okay, so here is our final example, okay, that we're going to look at. We're going to find dy dx for this equation right here. Okay, remember that was from the first page of our notes, and I mentioned something like, what a crazy equation. Okay, that equation is this ellipse that you see in the picture. I do not expect that any of you know that that's the equation for an ellipse that's tilted like that, so that's not the important part. Okay, but we're going to find dy dx, and then notice I've got kind of this follow-up question. What is its value at 2, 2? So what's the derivative at 2, 2? What's the derivative at 1, negative 1? So I'm basically looking at this point right here, and the point negative 1, negative 1, and I'm going to use those.
So my mom will give me a ride today. So when they're going in.
Okay, sorry group, his school is over today, so I had a couple people stop in. My apologies for that disruption. Okay, so I'm back to this. Here's the point 2, 2. So I feel like we're going to have some type of a derivative there, so we need to know what would be the slope of the tangent line. But then at 1, negative 1, right at this spot, we're going to have a totally different piece. And although when x equals 2, there's actually 2 locations on here, so we would have 2 separate derivatives when x is 2. Same with x being 1. At this point, I'm only caring about those particular spots on there. Okay, so we're definitely going to need to see that there's a derivative that contains both an x and a y variable. All right, so here we go. We're going to bring this, I'm going to bring this equation back down here so that we have some space to write. We're going to take a couple of minutes and go through this particular derivative. And I think this might be one of those problems that will be helpful also just to take up. Okay, I've seen 3 different examples and I sort of understand a little bit better. But we'll have more tomorrow, so hang in there. Okay, derivative of the first. Okay, this is an x term, so we're just going to follow our power rule. 10x is the derivative of that. Okay, then we move to our second piece. Okay, we're looking there. All right, so this middle term, we have another one of those problems that look like the last one. We're going to need to do a product rule. Okay, so the derivative of the first is minus 6 times the second, and then plus the first. Okay, and since that's also negative, I'm going to put a negative there as well. And then the derivative of the second, so dy dx. So this whole 2 terms that I just wrote down are all from the product rule. Now plus, and I'm sorry, I'm going to run out of some space here, but it's okay. Now this last part here on the left, y, remember, is a function. So for me to take the derivative of that, I'm going to go 10 and then y, which would be technically to the first power, and then I'm going to tack on dy dx. So just if this helps, in general, anytime that you are taking the derivative of a y, there better be a dy dx there. Sometimes it's the only thing because it's just a y. Sometimes it's tacked on because y was a gut. I don't know if that statement's helping everybody do the aha moment, okay, but that's what we need. And then derivative of 16, which is constant, is 0. Okay, so now we've got this. Now at this point, since we're asked to find dy dx, I'm going to take a moment here and get dy dx by itself. This third term and the fourth term both have a dy dx, so I'm going to leave those, and I'm going to move the things that don't have dy dx to the other side. So I'm going to subtract 10x, and I'm going to add 6y. So on this side, I still have this negative 6x dy dx plus 10y dy dx. And then on the other side, I have a 6y minus 10x. 6y minus 10x. So I added the 6y, subtracted the 10x. Now, because I've got a dy dx in common on the left side, I'm going to factor that out. So I just have 1 dy dx, and then I'm left with negative 6x plus 10y. It's kind of a coincidence right now that there's all these 6's and 10's. Okay, so that doesn't always happen. Very coincidental at this point. Okay, there's a little bit of some symmetry action happening, so it's not also a surprise. Okay, my last step is I'm going to divide then on both sides. Okay, so I end up, dy dx equals out to be 6y minus 10x over negative 6x plus 10y. Okay, so this is our derivative. And once again, you guys can see, like I talked about in this last problem, that it's no surprise that we got x's and y's in there. Because every point on this ellipse, it's important that we have both of those pieces because there's more than one a type of point on every x value. Fails that vertical line test. Okay, so now my question that I had before when we started this problem is, what is the derivative at 2, 2, and what is the derivative at 1, negative 1? So let's go back down here and say, what is dy dx? I'm going to use just a little bit of notation here at the point 2, 2. So remember early on we talked about Leibniz notation. We talked about this line and this bar. We haven't done that too much, so I'm going to do that so you're comfortable with that. So what is the derivative at the point 2, 2? So I'm going to plug in a 2's all around. Certainly you could do some of this in your head. We're taking some notes and watching the video, so I'm going to make sure that everyone's got at least a visual written. And we've got 12 minus 20, so we have a negative 8 on top, and we have negative 12 plus 20, so I have a positive 8 on the bottom, which gives me a slope of negative 1. And if I were to look back at my graph and think about, does that make logical sense? Here was that point 2, 2, and I could probably safely say that the slope of that tangent line is negative 1. And I would be comfortable saying that. Definitely, I did not draw a good negative 1 slope there. Okay, but you have the idea. So that should make sense. And I would definitely say, just looking at those 1, negative 1, that I better get a positive slope that happens there for that piece. So as I go down and then just test out my dy dx at the point 1, negative 1, I'm going to get 6 times negative 1 minus 10 times 1. And then on the bottom, I have negative 6 times 1 plus 10 times negative 1. Be careful about those x's and y's. Okay, they flip-flop. Plug those in correctly. On the top, I get negative 6 minus 10, so a negative 16. And on the bottom, I also get negative 6 minus 10. So another negative 16, and I come out here with a positive 1 slope. And I definitely feel pretty comfortable that I should have gotten this positive 1 slope at this particular point, 1, negative 1. Notice also I didn't ask in the directions, but I've got the slopes that I need and the points at that spot. So I could take that information and write the equation of the tangent line. So that could easily be, and hint, hint, will be some of the stuff that you're going to need to identify and write down in some of your homework pieces. What's the equation of the tangent line? Okay, but most importantly right now, we really need to be able to do and find this dy dx. Okay, so you got 3 good examples right here on some of that work and understanding some of those ideas. Tomorrow we're going to add some more to it. Okay, so what we want you to do is to take out the one worksheet, okay, and I think the first one that we're going to have you guys do, now I can't remember what we wrote down. I'm sorry, you guys have 2 implicit differentiation worksheets, and Holmquist is probably going to kill me because I should know which one's going first and which one's not. But work on the one that's in Canvas, that's following up this, starting on that, and then we'll see you again tomorrow for the second half.